In this video, we'll talk through Theorem 2.8 and discuss what it means for a bound to be sharp. And before we do this, we'll take a look at a couple examples of diameter and radius. So this is the theorem we're getting at, Theorem 2.8, that for every non-trivial graph, the diameter is at most twice the radius. This first inequality is immediate from just the definition of radius and diameter. It's included in this theorem for posterity, I guess. But the big result here that we want to prove is that diameter is at most twice the radius, right? And this is true in a circle. Well, I guess in a circle with diameter and radius, right? The radius is, the diameter is always exactly twice the radius for graphs. That's not true. So this isn't an exact analog of diameter and radius from circles. But nevertheless, this inequality holds and sort of justifies our language. So before I get into this theorem and how to prove it, I want to look at a couple examples. So I want to dive further into this relationship between diameter and radius. So I want to look at a couple families of graphs. In particular, I want to look at P2K and P2K plus 1. So that is even paths and odd paths. So for k equal 1, we're looking at the graph just P2, which is this one. I'll look at k equal 2 as well, and then sort of in general. So this would be path of length 3, 4 vertices. And here, my smallest one, I'll start at k equals 2 here, because k equals 1 is just a single vertex, and that's not going to help us. So this would be a path of length 2. K equal 4 would be path of length 4. Right, odd number of vertices. And I want to think about, what's the diameter and radius of each one of these? So for each vertex in each of these graphs, I'm going to compute the eccentricity. Here, the distance between this vertex and any other vertex is at most 1. Eccentricity of both of these vertices are 1. That's not going to help us out too much. K equals 2, though, so the distance from this vertex to any other distance, 1, 2, 3, that's the furthest. This is eccentricity 3. Eccentricity 3, these are antipodal vertices, remember? And then distance from this vertex to any other distance, any other vertex is at most 2. So those are eccentricity 2. So here the diameter is equal to the radius. Here we have that the radius is 2, right? The radius is equal to 2, and the diameter is equal to 3. So we have that the radius is strictly less, the diameter, I want to say that the diameter of that graph is strictly less than twice the radius. And indeed, if we jump up, let's jump up one more, k equal 3, 1, 2, 3, 4, 5, 6. Then, let's see here. Right, so this will have 1, 2, 3, 4, 5. It takes 5 to get there. That's the eccentricity of that vertex. 5, 1, 2, 3, 4 would be a vertex furthest, so this would be 4, 4, 1, 2, 3, 1, 2, 3, 3. So the diameter of this graph would be equal to 5. The radius is 3. So again, we see that the diameter is strictly less than twice the radius. And now let's take a look at some even paths, paths of even order. So for some paths of odd order, even length. For k equals 2, we can compute the eccentricities. This is 2, 2, 1. That's eccentricity 4, 4, 3, 3, 2. And maybe let's do one more. K equals 6. Oh, sorry. This is k equal 3. Let's do k equal 4. Oh, I have this all messed up, don't I? This is k equals 1. Sorry. K equals 1, k equals 2, k equals 3. So I should have 7 vertices here, as I do. 1, 2, 3, 4, 5, 6. Take 6 to get there. These are antipodal vertices. 5, 5, 4, 4, 3. So here we have the diameter of the graph is 2. Radius is 1. And so twice the radius is equal to the diameter. Again, here this is diameter 4, radius 2. So again, the diameter is twice the radius. And same thing down here. Diameter is 6, which is twice the radius 3. So here's 2 infinite classes of graphs. And hopefully you can see this is going to continue on in general, that the diameter will always be strictly less than twice the radius for these paths of even order. And for the paths of odd order, diameter will always be equal to the radius. So I bring this up because of, this theorem. What this theorem is saying that in general, the diameter is always at most twice the radius. So here we have an infinite class of graphs in which they're equal. So the theorem's still true. It's at most twice the radius. In fact, they're equal for this infinite class of graphs. Here, it's strictly less than that for this infinite class of graphs. So the point here is that this bound, diameter being less than or equal to twice the radius, that this is a sharp bound. That is, it cannot be improved. Right? That is, there are graphs, and even more so, not more than just there's at least one graph that's exactly twice the radius, but there's an infinite class of graphs for which these two things are equal to each other. And so that is, I can't have a theorem with the same assumption for all non-trivial connected graphs that improves this bound at all. I can't improve this in general. But there is an infinite class of graphs for which this bound is not the best possible for that infinite class of graphs, but for this hypothesis, for in general, this bound cannot be improved. And so we would consider this a sharp bound. We would consider a bound to not be sharp if for all graphs the diameter was strictly less than twice the radius. There we could actually improve the result. If we did a little more work with the proof, we could improve the result and make this strict. So what this is saying, this fact that it's sharp, is saying we cannot improve this bound. This is sort of best possible. Okay, so let's actually prove this result now. And I'm going to jump up to this example I had from the last video to sort of motivate the idea here. So I have this central vertex V6, right? So between V6 and any other vertex, the distance is at most 2. And then I also have these antipodal vertices, U1 and V8, right? Or V1 and V8, that are at such that the distance between them is the diameter. So, what I want to do here, V6, so the distance between V6 and a furthest away vertex, that gives me the radius of the graph. And so I'm going to use this idea. I'm going to look at central vertices and antipodal vertices. So let's prove this. Right, as I said before, radius of G is less than or equal to diameter of G. This, again, follows directly from the definition of each, right? Radius was the minimum of all the eccentricities. Diameter was the maximum of all eccentricities. So the minimum of a set is certainly less than or equal to the maximum of a set. So this is immediate. I really want to prove this inequality. So I'm going to let U and W be antipodal vertices. Remember what that means, that the distance between U and W is equal to the diameter of the graph. And I'm going to let V be a central vertex. So remember, what central meant was that the eccentricity of V is the minimum of all the graphs. It's the eccentricity of V is equal to the radius. Eccentricity of V is equal to the radius of G. And I'm going to use the triangle inequality again. So by the triangle inequality, I know that the diameter of G is equal to the distance between U and W, and now I have this third vertex, and so the distance between U and W is at most distance between U and V plus distance between V and W. And now I have two distances involving this vertex V, which is central, right? Its eccentricity is equal to the radius of the graph. In particular, the distance between V and any other vertex is at most its eccentricity, and hence at most the radius of the graph. So this is less than or equal to diameter of G plus diameter of G. Right? This is less than or equal to the diameter. This one's less than or equal to the diameter. And that's twice the diameter of G. Sorry, not diameter, radius. Let me repeat that last bit. Right. The radius is the eccentricity of V. In particular, the distance from V to any other vertex is at most the radius of the graph. Right? So this is less than or equal to the radius of G plus the radius of G. That's 2 radiuses of G. So diameter of G is at most twice the radius of G. And again, this result, so we proved it, this result cannot be improved without modifying the hypotheses, without restricting ourselves to a certain class of graphs besides non-trivial connected graphs. Okay, that's it for this one.